Okay, in chapter 7, we are starting by looking at what we call the addition formulae, or the sine A plus B, cos A plus B formulae. And there's 6 of these, the sine, cos and tan, with pluses and with minuses. Okay. Now, the first 2 of these, sine A plus B and the cos A plus B formulae, we can prove, but if you have a look in example 1 in the textbook, that's how we prove them. We start with this horrible looking diagram. This length here is 1, and then we've got this is our alpha, this is our beta, so this angle here is alpha plus beta, and then we use sort of similar triangles and all sorts of things, and eventually you end up with these things. Now, that's a nasty fiddly proof, and in the interest of sort of getting our way through the chapter a little bit more fluently, I'm going to miss those out, and I'm going to start by assuming these sine A plus B and cos A plus B formulae, and we're going to move on from there. Now, if at some point when I've finished filming the rest of the whole book, it's frustrating that that proof isn't there on these videos, by all means leave me a message, and eventually in months and months I might get around to it. But for the moment, let's just get used to what these formulas are and the way that they work. So, the sine A plus B formula, the way I remember it is the sine one goes sine cos, and then we get sine A cos B, and then this one must be the other way around, so this must be sine B cos A, and there's a plus sign in the middle. Okay, so sine, I always remember the sine is the nice one because there's a plus sign here, there's a plus sign here. With the cos one, the way I remember it is it's cos, sine. So it doesn't matter where I put the A's and the B's, because A and B either way is cos A times cos B, and either way here as well. But if with cos it's not as nice, so that plus there becomes a minus there. So cos minus sine. Now, before we look at what happens when this is sine of A minus B and cos of A minus B, let's just remind ourselves of these facts. First of all, cos of minus x is the same as cos of x, and you can see that by thinking about a cos graph. Cos of minus x is what we get if we reflect the cos graph in the y-axis, and the graph looks the same. If we think about the sine graph, sine of minus x, if you reflect the sine graph in the y-axis, then you end up with this thing here, this dotted line, which is the same as the sine graph, but we need to reflect it in the x-axis as well. So if I take the sine graph, reflect it in the y-axis, and reflect it in the x-axis, then I end up with the sine graph back. In other words, sine of minus x equals minus sine of x. Okay? This is a reflection in the y-axis, this is the reflection in the x-axis, just from graph transformations. So if I now think about sine of A minus B, that's the same as sine of A plus minus B. So everywhere in here that I had a B, I can replace it with a minus B, and it's going to work like this. So sine of A cos of minus B plus sine of minus B cos of A, and then cos of minus B is the same as cos of B. Sine of minus B is minus sine of B. So we can get that formula, that identity rather, that way, and you can get the cos of A minus B in exactly the same way. Change the cos of A minus B into cos of A plus a minus B, and then take this thing here, and every time you see a B, replace it with a minus B. Cos of minus B is the same as cos of B, and sine of minus B is the same as minus sine of B. So that's where we get the first of our, the first 2 of our formulae here. You're going to just have to trust me for the moment. These 2 we get in that way. Now the tan ones we can prove without it being too much of a hassle. It's a bit of algebra, but tan of A plus B is going to be sine of A plus B over cos of A plus B. So sine goes sine, cos, A and B. There I've got sine of A, so here I must have sine of B, and cos takes the other one with a plus sign in the middle. Cos of A plus B is cos minus sine. There's a plus sign there, so there's a minus sign there, because cos goes the opposite way around to what you think here. So A and B. Now, this is tan of a plus b, so I want something to do with tans. So if I divide through by cos a cos b, then I'll create some tans, won't I? Because every time I get a sine over a cos, I'll create a tan. So if I take the top of this fraction and the bottom of this fraction and I divide by cos a cos b, then let's see what we get. So I divide by cos a cos b, divide by cos a cos b, and that's going to be the numerator. All of that divided by cos a cos b, divided by cos a cos b. Finally, well, that one's going to be 1. Sin a sin b, divided by cos a cos b. Well, that's going to be tan a tan b. Okay, because sin a divided by the cos a gives me tan a, sin b divided by cos b gives me tan b. So it's just this bit to sort out. Well, the cos b's cancel out there, and the cos a's cancel out there. So this is sin a over cos a, this is sin b over cos b, so this is tan a plus tan b divided by 1 minus tan a tan b. Okay, so we've shown that this is equal to this. Not a particularly nice identity, not particularly sort of neat or memorable, but there it is. That's the formula that we've got. And then with the minus signs, we use the same sort of trick that tan of minus b is minus tan of b. Okay, so that's where we get all of these identities from. Now, once we've got these identities, if you start looking at the kind of things they ask us to do with them, guess what? Prove a trig identity. And basically, the kind of questions they've asked us to do already, do them again, only with the new identities thrown in. So here, this isn't quite a trig identity, but it's given that expressed tan x in terms of tan y, so change this into things to do with tans, and I've got a sin x plus y and a cos x minus y, so use the formulas, and then everything cancels out. Then do some divisions so that you've got things to do with tan, so divide by cos x, cos y, and then you get expressions in tan. Now, I can't give you a sort of a list of the applications of these things. It's like all the trig identities we've seen so far. There's a bunch of new trig identities, and we need to apply them for the kind of questions that we've got. So guess what? We're going to be solving trig equations. We're going to be simplifying expressions with trigonometric identities in them, and we're going to be proving trig identities again. Okay, so that's everything really for exercise 7a. It's just getting used to these things. Here we've got, this is sine cos, cos sine, so that's going to be like a sine a plus b formula, and the a and the b are going to be the 15 and the 20, and so all of these ones are sort of rigged up to look like that, and then we end up with things with, with particular values in there as well. So if we put pi by 2 and a theta in there, then we can finally prove this sort of thing, which we've known for a while, because if you think about it, pi by 2 minus theta, if you've got a right angled triangle, this angle is pi by 2. If this is theta, this is, well, 180, or pi, take away pi by 2, so these two add up to pi by 2. So this is pi by 2 minus theta. So cos of this one is equal to sine of this one, and we kind of know that to be true, and we can prove it this way if we wish to. So it's just getting used to the identities that we've got, and I'll move on to section 7.2 in the next video and show you a few more of these sort of applications.